Hello, my name is Doga Tekin. I'm a member of technical staff at Oracle Labs Zurich. Thank you for joining this session on transforming text documents to graphs. This was a collaboration between Oracle Labs and Oracle Financial Services. And I will start by introducing what knowledge graphs are. I will give some motivating use cases for why we might want to transform text documents to knowledge graphs. I will go through some related work and state of the art. I will then explain the approach that we've built for doing this transformation from text documents to graphs. I will quickly describe the data sets we've focused on in the science domain and in the finance domain. Then I will bring you some experimental results that we obtained and show you a visual demonstration of this process. I will summarize with some points, and I will give a teaser on some ongoing and future work we have at Oracle Labs on the same topic. So let's start with an introduction on what knowledge graphs are. Knowledge graphs are a way to store knowledge that uses a graph structure to represent information about entities and relations. Here's a small example knowledge graph based around me. You can see there's a node for Doga Tekin. You can see that this node has a connection to Oracle Labs with a works at relation, and there's a connection to Zurich with a lives in relation. So you can see that a knowledge graph is a quick way to obtain information about different entities and their relations between each other. They're useful for many applications, including in search engines, in smart assistants, in detecting fraud, or in healthcare. You can follow those links on the slides to obtain more information. They are performant and they're expressive. They allow you to integrate and unify lots of different types of data, and they let you analyze that data in useful ways, hence why they're so popular. So that might already be enough motivation for trying to transform text documents to graphs, but I would like to give some practical reasons as well. One is just visual inspection. Sometimes seeing information presented graphically as connections between nodes, this can help us see patterns that are easy to miss in plain text. And the second reason is to empower some downstream tasks and algorithms. There's a lot of research and there's a lot of algorithms that were developed to process graphs in smart ways. And obtaining a graph representation of information is the first step in being able to apply those powerful algorithms. Here's some example use cases. Let's start from the literature. There was an effort in 2018 by this research group to obtain a scientific knowledge graph by reading paper abstracts and parsing them automatically. So this looks like this. By reading an abstract of a scientific publication and specifically detecting what techniques were mentioned in this paper and what they were used for and what techniques were used for these techniques, they were able to obtain graphs of each scientific paper abstract. And by combining these graphs from different scientific papers, they were able to get these high-level views on these publications. So in this graph on the right, you can see statistical machine translation. It uses these different techniques. It's used for these different tasks. It's evaluated by these metrics. So this was an automatically constructed graph explaining a lot about the publications at that period. In our case, we're interested in a different task from the finance domain. We're interested in case graph construction from suspicious activity reports. So suspicious activity reports are these little reports that are filed with investigation bodies that explain some suspicious activity regarding a customer or regarding their accounts or regarding some transactions that are going on. This is a small example excerpt from a suspicious activity report. And on the right, you can see a graph representation of the same information. You can clearly see what transactions this account is doing, who owns this account, what other persons or entities this owner is related with. So it's already maybe quite useful just from this example. So the task in this project is to go from the left image to the right image in summary. So we started this project by doing some literature review. And the first thing we found was this scientific knowledge graph construction task that I already presented an example of. This dataset is called SciArc for short. It consists of 500 scientific paper abstracts annotated with entity, relation, and coreference information. I'll explain briefly in the upcoming slides what these tasks are and why all these data annotations are needed, but all three tasks must be completed to obtain a graph from a text document. And if you quickly have a look at the results they obtained in this 2018 paper, you can see some F1 scores for each task that are around 60, 40, 50. So not very high scores. This is quite a challenging task. But the second thing we noticed was since the publication of this approach, there have been good improvements in all of these three natural language processing tasks. But there haven't been any new approaches bringing all these improvements together into a new improved text-to-graph pipeline. So that's what our goal was in this project. And in particular, the biggest impact on these natural language processing or NLP tasks since that publication was the introduction of transformer models, and most notably perhaps the BERT model. And when we did a review on all three tasks and looked at some recent papers and the F1 scores, how they developed over time, we saw that there were significant improvements, and the strongest models seem to often consist of large pre-trained transformer models similar to BERT, plus simple classifiers on top of them. So the aim was to obtain a state-of-the-art text-to-graph pipeline using these modern approaches in this project. So let's get to the actual approach. How do we actually go from a text document to a graph using these three NLP tasks? We start from sentences. A text consists of multiple sentences. The first step is each sentence is processed individually by an entity recognition model. This model tells us what types these entities are and which entities are found in each sentence. Then each sentence and its entities go through a relation extraction model. The relation extraction model tells us which types of connections and relations each pair of entities might have in this sentence. So at the end of these two steps, we have subgraphs that represent each sentence in the document, but we don't have the single unified graph. So the last step is coreference resolution, which tells us which entities from different sentences are actually the same entity in real life. So this information is the final part in obtaining this unified representation. I'll go through each task in a bit more detail. So this first task of entity recognition, from a human perspective, from our perspective, is just looking at a sentence and trying to understand where in that sentence relevant entities are and what type those entities are. So in this sentence, we can see Adam Smith is likely a person. The numbers at the end are likely a date. From a modeling perspective, there are different ways of doing this, but one way to do it is to break a sentence down into its tokens or words and classifying each token with a special label that can tell the model and that can tell us where the entities are and what type those entities are. So these special tokens you see at the bottom tell us the first two tokens constitute a single entity of the person type. Or at the end, the label says this token here is a date. And the other tokens in the sentence are not part of any entity, so they're labeled with this O label. And so that's the high-level approach of how to do NER. How do we do it in practice? Well, we use these transformer models that I mentioned. You can imagine what these transformer models do simply as taking in as input some tokens, a sentence, and producing a numerical representation of each token in that sentence. And these transformer models, you can see inside there's a lot of connections and parameters going on, and they usually have hundreds of millions of these parameters. And they often come pre-trained on a language modeling task that uses a huge data set of billions of words. And what that means is these transformer models are pre-trained to be able to capture syntactical and semantical information about whatever input tokens and sentences you give to them. So these numerical representations we obtain are quite meaningful and useful in understanding what this text is saying. So all we need to do is put any simple classifier at the end using these representations, and we can get these special tokens out of them for the NER task. And then all we need to do is to fine tune this whole system including the classifier and the transformer as an end-to-end task, and we often get quite good results. The next task is relation extraction. This one starts by taking a sentence and its entities from the last step, and this one is just trying to determine what relations there might be between any pair of entities and what that relation, if any, is. From a modeling perspective, what we have to do here is to enumerate each potential pair of entities in each direction, because each relation might be directed. So we have to go through each pair of entities, and we have to ask our model, is there a relation between this entity and this entity in this direction or in this other direction? And if there is, what is that relation? The way we solve this with transformers is quite similar to how we solve the entity problem. We start with a transformer, we go and pass our sentence through the transformer to obtain the numerical representations. So last time we used the word embeddings to make decisions about words. Now we need entity embeddings to make decisions about the relations of entities. So if an entity consists of a single word, like the account at the end here, it's easy to obtain the embedding. The word embedding is the entity embedding. And if an entity consists of multiple words, like Adam Smith here, to obtain the entity embedding, we simply average or aggregate in another way the embeddings of the words that constitute that entity. Now that we have both embeddings of these two entities, we can build another classifier that can accept as input two embeddings, the embeddings of the entities we're interested in, and ask this model, what is the relation between these entities? And if you want to know the relation in the other direction, we simply concatenate the entity embeddings in the other way. And then we again ask our model, what's the relation between these entities? And the final task is coreference resolution. And this is a bit more involved, but we can still go through it. And it's quite similar to the others in some ways. So from a human perspective, this is about looking at multiple sentences. So this is the first sentence that we've been using already in the other tasks. Let's say there's a later sentence in the document that again mentions Adam, that again mentions the account. When we transform this text document into a graph, we don't want to have one node that says Adam Smith and another node that says Adam. We want to know that these refer to the same person in real life. And we want to similarly know that the account number refers to the account later on. So the way to do this is in two steps. First step is to find what we call mentions. Mentions are spans of words in a text that might be referring to an entity in real life. Again, here's the same transformer model we've been using. Let's focus on a different example this time. Let's say a sentence is General Electric said the Postal Service contacted the company. What we need to do is we have to go through each span in the sentence, each set of words, basically. So some examples might be General Electric, Electric said the Postal Service, Service contacted the. So we have to go through each span of words, whether they make sense or not. And the model has to decide which ones are likely to refer to a real entity. So the Postal Service or the company are likely to refer to a real entity, but Electric said the is not likely to refer to a single entity in real life. The next step is, now that we have these mentions that were obtained using these transformer embeddings, the question we have to ask is, for each span, for each mention, what are the antecedents of this span? This just means what are the previous mentions that refer to the same entity as this one. To do this, we again use these numerical representations from the transformer, but we pass them through some scoring models. So for each pair of spans, we pass them through a scoring model to get the likelihood of those two spans referring to the same thing. And in the end, if we find that two spans are likely to be mentions, likely to be referring to the same entity, we can say that they probably are the same entity. And then we can do some final clustering step to know which spans in this document refer to the same entity. So we've used several public datasets to validate the performance of our specific models and framework. Some of these include the ones on the screen. We've used named entity and relation extraction datasets. We've used coreference resolution datasets. And we've, of course, used the scientific knowledge graph construction dataset from earlier. Additionally, we also wanted to test text to graph in the financial domain for our use case that I presented at the start. For this, this is the same excerpt from the beginning of the presentation. We had 100 of these suspicious activity reports, and we had to annotate them to be able to train our models. So we set up an annotation tool, and we had to go through actually 2 subject matter experts that we were working with from Oracle Financial Services, helped us go through these documents and annotate all the customers, all the account numbers, all the occupations, and all the relations between all these entities. And of course, the coreference relations. So how did we fare on the scientific data set that we were trying to improve upon? We've actually improved quite a bit on all 3 tasks using these modern methods, with anywhere between 6 to 12 absolute percentage points was gained in these tasks. And I should note at this slide that there are actually even better scores published for individual tasks on this dataset. There are better NER results on this dataset, or there are better relation extraction results. But among frameworks that tackle this end-to-end task of doing all 3 things and obtaining a graph from the text, at the time of our research, these were state-of-the-art results on this dataset. And going to our dataset, the scientific suspicious activity report dataset, we saw that the metrics were even higher. And the reason here was the suspicious activity reports we were using were synthetic, and they were more structured documents. So the models had a much easier time exploiting that structure and knowing and learning which entity will appear and where relations will appear. And we've also made sure that these natural language processing metrics translate into a high quality graph. So we've also looked at how many of the nodes and how many of the edges that we wanted to capture are actually captured correctly. Here's how the demo looks in an end-to-end way. There's a text box. You input whatever text you want to obtain the graph of. First, you get a visual output of each entity that was detected, each relation that was detected, and the coreference links. Secondly, you get the actual built graph that you can play around with and visualize. I'll go through step by step on what's going on in this demo. So when you give a text, the first thing that happens is it's broken down automatically into sentences, because some models process sentence by sentence. The second part is all sentences go through named entity recognition and relation extraction. You can see each entity in each sentence is labeled with the correct type, and you can see the relations between the relevant pairs are shown, and what relation type is detected is shown. And at the end, we see the coreference resolution clusters that are found. It tells us which entities from different sentences are likely to be the same entity. And finally, this graph is built. The demo here is using also Oracle Labs products. So we're using PGX to represent the graph and Data Studio to visualize it and make this interactive notebook that works to give us this demo. So just to summarize and conclude slowly, we've achieved new state-of-the-art results in this end-to-end text-to-graph task by combining modern entity recognition, relation extraction, and coreference resolution approaches. We constructed a fully annotated financial dataset for the task. We've compared different approaches on multiple datasets, and we created an interactive notebook that transforms input text into a graph, at least in the financial domain. I just want to end with a teaser on some ongoing work we have in improving all of these things. We think the inverse task of transforming graphs to natural language text is also interesting to generate reports and summaries of case graphs after investigations, for example. We think techniques to reduce the manual annotation efforts of going through 100 documents and marking all the entities and relations, it would be valuable to try to reduce this effort. We think using a single transformer model instead of a pipeline of 3 separate models could bring speed and accuracy benefits. And in addition to capturing edges of the graph, so relations between entities, it would also be interesting to capture properties of those edges. For example, the amount property of a transaction edge between 2 different accounts. This would be a useful extension. So we have some ongoing work on training both a text-to-graph model and a graph-to-text model together at the same time. This is based on a concept called cycle training, because these 2 tasks are kind of dual tasks. You can go from a graph to a text using a graph-to-text model. You can go back from the text to a graph using the text-to-graph model, and you can see if you obtained the same graph as you started with. And this gives you a loss that you can try to reduce and optimize. And vice versa, you can do this from text to graph to text, and you can use that cycle loss as well. The way we're working on this right now, we are using a single transformer for the entire text-to-graph task and one for the graph-to-text task. And this also has the potential to capture more information from the text, including edge properties. And also importantly, this approach only requires you to have a set of text documents and a set of graphs that you can do the cycle training on. So this might remove the need for these fine-grained entity and relation annotations that we had to do earlier. So hopefully by next CloudWorld, this will be the interesting work that we will be able to present to you. So thank you a lot for joining. I would also like to thank all the collaborators we've had on this project on Oracle Labs and also from Oracle Financial Services. Feel free to reach out to me with any of your questions about this work or our ongoing work. And thank you again for listening.